Okay, so what we're going to start working on today is we need to start graphing polynomial functions without using our calculator. And I know the calculator there is nice, it's helpful, but we're going to have to start practicing and learning how to do this skill without using it. So first thing is this is the generic formula for a polynomial function, which I don't know about you, but whenever I look at it, I hear like the teacher's voice from Charlie Brown going wah, 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 wah. It is very confusing. So this just, exponent, this is referring a sub n, that is your coefficient. So we're going to be looking at our exponents and our coefficients here. So the first thing we're going to start practicing with today is looking at end behavior. So we're going to be looking at the end behavior of our polynomials, but in order to do that, we need to be able to identify three things from the equation. So the first one is the degree. Now who remembers what is the degree of a polynomial? The largest exponent that we have there. So my first example here, what degree would this one be? 3. Largest exponent there is a 3. That is a third degree polynomial. Next thing we have to be able to pick out is our leading coefficient. So that is just the coefficient of the term out in the front. So what is our coefficient of our first term there? -1. And then the last thing from our equation is the constant. What would be our constant value here? 1. Anybody think they know off of the graph what the constant value represents? Okay. That's the y-intercept. Perfect. So you can always tell quickly from your equation where your y-intercept is going to be because that's always your constant term. If I don't have a constant term, what is my y-intercept? 0, because there's nothing there. So let's take a look at our next example. So what degree would example number 2 be? 4. Our leading coefficient, 1/3. And then our constant term, -1/2. So those two examples, those were in standard form, pretty easy. You find the largest exponent, and then you use that term to help you figure out your degree and then your leading coefficient. The other way that our polynomial functions could be written is in factored form. So our next two examples are polynomial functions written in factored form. So when it's in factored form for your degree, what you want to do is you're going to add the exponents. So if your polynomial is in factored form, you add those exponents. So for this example number 3, our exponents would be a 3. There's a 1 here, and then a 2. So we add 3 plus 1 plus 2, so that makes this a 6th degree polynomial. Now, if you did have exponents inside the parentheses, you would have to take those into consideration also, but these ones were all exponents to the first power, so the ones on the inside didn't matter. It was just those ones on the outside. Our leading coefficient, so for our leading coefficient, you're going to multiply all of the leading coefficients from your factors. And I just shortened leading coefficient down to LC. So LC stands for leading coefficient. So you're just going to multiply each of those from the different factors, keeping in mind what those exponents are on the outside also, because that's going to play a role in it too. So if I look at my first parenthesis here, my leading exponent would be that 1, but it's to the 3rd power. So it's going to be 1 to the 3rd power times my leading exponent in my second parenthesis is a 1, but that one was to the 1st power, so that's going to stay as 1. And then my third set of parentheses, my leading coefficient was a 2, but that's squared because it's got that exponent 2 on the outside. So now we got to multiply these together. 1/3 to the 3rd times 1 times 2 squared. What does that give us? 4. Because 2 squared is 4 times 1 times 1, and it's going to say is 4. And then our last one, our constant, same process as with our leading coefficients, only you're going to use the constant terms at the end. So from the first parenthesis, that would be 2, and then it's going to be cubed times the negative 1 from the second parenthesis, and times the positive 1 from the last squared. So our constant term ends up being negative 8, because 2 cubed is 8, times the negative 1 makes it negative 8, and then 1 squared is positive 1, so it doesn't change it. All right, so let's try it again with the next one. So again, inside all of our parentheses, exponent of 1. So to figure out our degree, we're just going to add all those exponents on the outside. So 3 plus 1 plus 2. This one ends up being a 6th degree again. Not always going to end up being a 6th degree. That's just coincidence. So then our leading coefficient. What is our leading coefficient from the first set of parentheses? Negative 1, so that's going to be cubed. Leading coefficient from the second parentheses, 2. And then leading coefficient from the third, negative 1. It's always that number in front of x. That last set of parentheses is not in the correct standard form. It should be negative x plus 2. So this one, when we multiply this one here, that's squared, that turns positive. This one stays negative, so negative 1 times 2 gives us a leading coefficient of negative 2. So then our last one, our constant term from the first parentheses would be a negative 1. Second parentheses would be another negative 1. And then the third parentheses would be a 2 squared. So what does that end up giving us? 4. Other thing, kind of refresher, symmetry. We've talked about symmetry in the past in our functions unit. So functions can have even symmetry, odd symmetry, or neither. So if it has even symmetry, what is that symmetric over? The y-axis. And then odd symmetry is symmetric over, that's inverse line, the origin. So symmetric through the origin for odd symmetry. So if they give you a picture of a graph and they tell you what kind of symmetry it is, you should be able to draw the second half of the graph. Now my graphs, my lines are kind of messed up, but if you can find some nice even points in there, like let's see here, the point 1, 2, right here. So you would have the point negative 1, 2 for even symmetry. And let's see here. This one should be over here. Then we sketch our other half of the graph. So then for our odd, we got this point here at negative 1, negative 2. That means for odd symmetry, we would have one at positive 1, positive 2. Change your sign values. This one looks like it hits at like negative 2, positive 2. Does it? That'd be positive 2, negative 2. Then you can draw the other half of your odd symmetry. So on the top of the next page, go ahead, type those in your calculator, draw a sketch of it, and then determine whether it's even symmetry, odd symmetry, or neither. That's our even, and that's our odd symmetry. So it's even and odd symmetry is a little different than an even or odd degree. Just because you have an even degree does not mean that your function is going to have even symmetry. Those are kind of two different things, although they do use the same words. Same thing, odd degree does not mean it's necessarily odd symmetry. So figuring out the end behaviors. There's always a pattern that arises when we're figuring out our end behaviors. So if n is an even, so if we have an even exponent, like y equals x squared, y equals x to the 8th, if you have an even exponent and your leading coefficient is also positive, your end behaviors are going to both go up. Always. So even degree, positive leading coefficient, end behaviors are going to go up. So now the way that we write this, we have to get a little fancier with our writing now. Instead of saying left side, right side, we have to use this notation. X approaches positive infinity. This means the right side. And then as x approaches negative infinity, that's referring to the left side. So that's our new notation now for right side, left side. So as we're going either to positive infinity or negative infinity, which way is the graph going? Yeah, the graphs on both sides are going up. So as x is going to positive infinity or as x is going to negative infinity, y is going to positive infinity, y is going up. So then if we have an even degree with a negative leading coefficient, so like for example y equals negative x to the 4th, do you guys remember which way those ones go? Like if we had negative x squared, it goes down. Yeah. So no matter what your even degree is, if your leading coefficient is negative, your end behaviors are both going to be going down. So again, in our new fancy notation, as x goes to positive infinity, or as x goes to negative infinity, the graph y is going to negative infinity. So again, positive leading coefficient, even degree up, negative leading coefficient, positive degree, or even degree going down. Both up, both down. So in looking at our odds, if we have an odd degree, so as for example, y equals x third, y equals x to the 5th, you have a positive leading coefficient, the way our end behaviors are going to go is the right side's going to go up and the left side's going to go down. So we would write it as x goes to positive infinity, y goes to positive infinity. The left side is x goes to negative infinity, y goes to negative infinity. Remember, you don't have to put the plus signs in there for the positives. That one's fine. You definitely got to have the negatives, though, for the negative infinity. So then if we have an odd degree with a negative leading coefficient, so like for example, y equals negative x to the 7th, our end behaviors are going to flip-flop. So left side would be up, right side's going to end up going down. So I find that the odd degrees are the ones that are a little trickier to figure out. The evens are pretty easy. They're either both up, both down. So a little pattern that I've noticed with your odd degrees, if you connect the two tips of your arrows, it makes a line. This one is a positive sloping line, so that means your leading coefficient is a positive value. Whereas with this one, if you connect the tips of your arrows from your end behavior, you get a negative sloping line, so that is the one that has the negative leading coefficient. So it's just a little pattern to help you remember which one is going to end up being which. So we're going to practice this because this is sometimes the hardest thing. So we're going to describe the end behaviors. So to figure out our end behaviors, we got to look at two things. The degree and then what the leading coefficient is. So what is our degree on the first one? Degree of 3. Largest exponent there is a 3. Leading coefficient is a -1. So that means we have an odd degree with a negative leading coefficient. So that means it's going to end up looking like that. So now we just have to get our correct notation for it. So my right side is x goes to positive infinity. My graph is going to negative infinity. And this time we have to write f of x because that's what the equation is. Then our left side is x goes to negative infinity. The function goes to positive infinity. All right, so let's go to the second one, right below it. We're going to do the left side, and then I'm going to have you try the right side. So number 2 is not in correct standard form. So I recommend rewriting it in standard form so that you can figure out your degree and your leading coefficients. So it should be negative x to the 6th minus 5x plus 4. So our degree is what? 6. Our leading coefficient is -1. So we have an even degree, negative leading coefficient. So that means it's going to be, both sides are going to be going down. My right side and my left side. Function is going to be going to negative infinity. All right, that third one, what's our degree? 55. So our leading coefficient, -1. So a negative odd function again, that means left side is going to be up, right side is going to be down. All right, number 7 there is in factored form. So we got to add our exponent. So what is our degree for number 7? One plus 3. We got a degree of 4 there. Our leading coefficient. This time we got that -2 out in front. We didn't have those in my other examples. That's part of your leading coefficient. So we got a -2 times 1 times 1. So our leading coefficient is going to be that -2. So I have an even degree, negative leading coefficient. That means both sides are going to be going down. All right, number 9. That x out in front does get included as part of your degree. So this x has an exponent of 1, plus 1, plus 2, plus 1. This has a degree of 5. That x is still part of it. If we wanted to get technical, it would be written as x plus 0 with an exponent of 1. So that exponent is still included. Our leading coefficient, positive times positive 1. This would become positive 1. Times another positive 1. Our leading coefficient would be positive 1. So odd degree, positive leading coefficient. The left side's down. The right side's up. All right, go ahead. Try those ones on the right side. I'll be walking around to give you some help. There's the 5th one. That's an even degree with a positive leading exponent, so both sides should be going up. All right, 8 ends up being an odd degree with a positive leading coefficient. So right side up, left side down.